So welcome back everyone to the fourth workshop of Advanced Track. So hopefully you guys are having a good week. So we are aware that there are you guys probably have midterms this week. So that's why we're going to try to keep this workshop a little bit shorter. All right, so last time we went over some basic architectures of or the basic structure of a CNN. And today we're going to be covering some more advanced CNN architectures like Inception, ResNet, and UNet. We're also going to be covering some other topics like pre-training and transfer learning. So these are not directly related to CNNs, but it's going to come in handy when we move into our guided project later in the workshops series. All right, so without further ado, let's start with a brief history of CNNs. So this is actually adapted from this article called Illustrated 10 CNN Architectures by Raimi Karim. So if you're interested, then feel free to check out this article. It definitely talks about these architectures in more detail, but we're going to just be covering these at a very high level today. Okay, so let's start with LaNet 5, which was created in 1998. So I'm not sure if this is the very first CNN that was invented, but it's definitely the one that popularizes the basic architecture of a CNN, and also introduces some important concepts like convolutions and pooling. So let's fast forward to 2012, which is when Alexnet was created. So this is the time when CNNs really took off. And the unique thing about Alexnet is it has more layers, and each layers have more filters. So what this enables Alexnet to do is to learn more complex features, or learn a larger number of more complex features. And Alexnet also introduces the ReLU activation, which enables faster training, and because the gradient of ReLU is pretty easy to calculate, and also avoids issues like vanishing gradients, which is especially problematic for a deeper architecture like Alexnet. Okay, so like I said, Alexnet was designed and named after Alex Krizhevsky from the University of Toronto, and was published with the paper titled ImageNet Classification with Deep Convolutional Networks. So Alexnet actually won the 2012 ImageNet Large Scale Visual Recognition Challenge, which was pretty cool. And it's also one of the most influential publications in computer vision. And it's been cited over 30,000 times, which is a testament of its pioneering nature in the field. All right, so let's look at the basic structure of Alexnet. So there are 5 convolutional layers and 3 fully connected layers, which are all at the end here. And ReLU is applied after each convolutional or fully connected layer, except for the output layer here, which I think softmax is being applied because we're doing multi-class classification. And in addition, dropout layers applied before each of the first 2 fully connected layers. So we haven't gone over what a dropout layer is, but it's basically a form of regularization to combat overfitting. And also max pooling is the pooling of choice here. Okay, there's no questions. Okay, so I'm gonna pause here for a second for questions, but I don't think we actually covered that much so far, so. Okay, all right, so before we get any further with more CNN architectures, let's do a quick review on the basic components of a CNN. So let's get started with convolutional layers. So the input to this layer is just the image, which is represented by this green 5x5 grid in the background. And the thing that is moving here is called the filter, which I guess you can think of as like a weight matrix, but one that you can reuse for like different neurons or different input neurons. And so what this filter represents is just like a feature that you want to detect from your image. So by moving this filter across your image and taking the element-wise product, so what you're doing here is you're just trying to extract the feature that is represented by your filter. And then the output would be your convol feature or just a feature map. So what this feature map represents is like a heat map of your feature. So if you see a 4 here, that means there's a pretty good match between the feature represented by your filter and the top left corner of this image here. Whereas if you have a 2 like here or even at the bottom, then that means there's not that big of a match. So yeah, that's basically how convolutions work. I see there's something in the chat. Would we know what the features? Okay, so usually like for the first convolutional layer, the feature is like pretty low level. So it might be like an edge or like a color gradient or a corner. But like, I guess actually like let's go through an example. So okay, let's say we're doing image or face recognition. So one feature might be an eye, which is something you want to detect from the face, and another thing might be like a nose or like an eyebrow. So these features would be represented by your filter. But yeah, like I said earlier, like in practice, like the feature that is actually being detected by your CNN would probably be something that is not like as nice. Like it might be just like an edge. So you basically have no control over what features actually being detected because like the filters are being learned by the network itself. So yeah, hope that answers your question. Like I guess if the question is like can you pick what feature is being learned, then the answer is no, because the CNN will basically learn what this feature is over the course of training. Okay, hope that answers your question. So let's move on to pooling layers. So last week we went over max pooling and average pooling, but in practice, max pooling almost always outperforms average pooling. So let's go through an example here. So let's say our feature map is 4x4, and we pick a pooling size of 2 and a stride of 2. So what we're doing here is we're partitioning our feature map into 4 subsections. And in each section, we're kind of just choosing the maximum value. So for example, in this yellow region here, we're picking the 6 because it's the maximum. And in this green region here, we're picking the 8 because it's, again, the maximum. So I think you guys get the idea. So when we apply pooling layers to our network, we generally have a few objectives in mind. So the first one is just to downsample our feature map, just to reduce the number of parameters that we have to deal with later in the network. And the second goal here is not as obvious, but basically when you do max pooling, you basically achieve like a partial invariance in like slight rotations or translations in your input image. So for example, if this 8 here is rotated slightly to where this 2 is, then the output of your pooling layer is still going to be the same. So this basically kind of like serves as a way to suppress noise in your, I guess, in your input. Okay, so the order here is kind of like weird because ReLU is supposed to come like between your convolutional layer and your pooling layer. But anyway, so ReLU, it stands for rectified linear unit, and it looks something like this. So ReLU is basically just a piecewise function that is gonna output x if x is positive and 0 if x is negative. So I think I mentioned earlier how the gradient of ReLU is easy to calculate. So this is what I mean here. So when ReLU is positive, the gradient or the derivative is just 1. And when it's negative, then the gradient is just 0. So, however, there is a slight issue here. Does anyone know what the issue is? There's an issue of doing backprop with ReLU. Yes, exactly. So ReLU is actually non-differential at 0, as you can tell from this graph here. There's also, because there's a corner. So, but in practice, this is not actually a huge problem because you can either set the derivative of ReLU to be 0 or 1, and backprop works pretty well empirically. So, yeah. Okay. So any questions about convolutional layers or pooling before we move on to like a code snippet? All right, I guess not. Okay, so here's an implementation of a CNN with PyTorch. So I think this is just like the constructor of a CNN where we define like all the different layers that we're going to be using. So yeah, I think we have like different convolutional layers with different, actually the filter size is the same, but I guess the input and output is different. And then we're using leaky ReLU here instead of regular ReLU, but I think it doesn't really make that much of a difference. And then, yeah, the thing here is we have these like fully connected layers at the end. And then an output layer, which is softmax. And so this is how feed forward is implemented with so after we create an instance of our CNN, then we can basically perform feed forward by just calling like the layers that we defined in the previous page. So yeah, we're definitely going to go into PyTorch in a lot more detail in our guided projects. So here's another implementation with CNNs with the Keras API from TensorFlow 2.0, just in case some of you come from a TensorFlow background. So I think, or at least in my opinion, the Keras API is a lot more beginner friendly because like all you're doing here is you're defining your CNN like sequentially. So first you add the first convolutional layer here. So we set the number of filters to be 32. The kernel size is just the dimension of your filter. So kernel size 3 here means we're using a filter of 3 by 3. And yeah, we're choosing ReLU as our activation function. There's another thing here, which is our input shape, because this is the very first layer. So we have to specify the input shape. But yeah, if you can see like below, like since these are like layers like after the first layer, then TensorFlow can kind of just figure out what the input dimension to that layer is just from like the layers that you defined earlier. And yeah, after adding our convolutional layer, we're going to be adding our first max pooling layer with a pool size of 2 and a stride of 2, which is, I think, what we're used to. And then it's pretty common for us to have multiple sets of convolutional and max pooling layers to extract higher and higher level features. So we can kind of think of this as like a hierarchy. So back to our face recognition example. So the first convolutional layers might extract like something really simple, like an edge or like a corner or some like color gradient. But like the second set of convolutional and max pooling layers might extract like something higher level, like an eye or like an eyebrow or an ear. So this is just like a good way to, I guess, think about why we have like multiple sets of convolutional and max pooling layers. So after that, we have to, flatten our the output of the max pooling layers in order to apply our fully connected layers. And our output layers here is just a sigmoid neuron, because I'm assuming we're doing binary classification. So the rest is kind of a standard. So we just compile our model, fit it, and predict it, and make a prediction. So yeah, any questions with regards to the code? If not, we actually have a poll question that is about on the implementation of the CNN on the previous slide. So I'm just gonna launch this poll here. Okay, I think you guys should be able to see the poll. So the question is, what is the shape of the input and the output of the first convolutional layers of the CNN from the previous slide? So this is just this is on the CNN implemented by the Keras API, so not the PyTorch one. And yeah, I think if you guys don't have, so I think most of you have access to the slides, but I'm gonna, this question might be a little bit tricky, so I'm gonna give you guys like a bit longer. All right, just in case some of you don't have access to the code. All right, I'm gonna wait for like 30 more seconds, I guess. There's something in the chat though. Okay. All right, I'm gonna end the poll in like 5 more seconds. Okay, so let's share results. So most of you got it right. So the correct answer here is C. I guess the reason why the depth of the output is 32 because we're using 32 filters. So if you remember, like the output of the convolutional layers is just, or the depth of the output is determined by the number of filters, which is 32 in this case. So yeah. Okay. So another notable CNN architecture here is the Google Net, which is the winner of the ILS VRC competition in 2014. So this is just like an image classification competition. And the innovative thing that Google Net did was it introduces these Inception modules, kind of a reference to a movie, but Yeah, so you can basically think of an Inception module as like a network within a network. So what do I mean by this? So let's look at this picture of an Inception module here. So the Inception module looks like a tiny or mini network itself. So you would expect these nodes here to be hidden neurons, right? But these are actually like full-blown convolutional layers. So what this essentially does is it creates like parallel pipelines of convolutional layers with different filter sizes. So what this enables an Inception module to do is detect like features with like varying sizes. Okay, so what do I mean by that? So let's look at these three images here. So the leftmost image is like a close-up picture of a dog. And the dog in the middle image here is like slightly further away. And the dog in the rightmost image here is like the furthest away. So as humans, we can easily tell like these are all like pictures of dogs. But unfortunately, our vanilla CNN actually won't be able to tell that these are all the same thing, just because like the size is different. So how does Inception tackle this issue? So basically, like we have like parallel convolutional layers with different filter sizes. So for example, like, okay, let's go back to the previous slide. So for example, like with this close-up picture of a dog, this might be picked up by our 5x5 filter or convolutional layer, while like these images of dogs that are further away could be detected by our 3x3 convolution or 1x1 convolution respectively. And there's also this max pooling layer here, which is in parallel with the entire network, which kind of just, I guess, downsamples the feature or the feature map. And I guess, yeah, the next CNN architecture that we'll briefly talk about here is the UNet. So yeah, as the name suggests, the UNet kind of looks like a U, which is a nice way to remember it by. So basically the task that the UNet does here is actually called semantic segmentation, which is different from classification, which is what we're used to. So the interesting thing about UNet here is it makes use of something called Transpose Convolution, which is to upsample our feature map. So this is different, or this is opposite to what we're doing with max pooling layers or just any pooling layers, which is to downsample our feature map. So why do we have to upsample our feature map? So this has to do with the task of semantic segmentation itself. So basically what we're doing with classification is we're asking the question like, is this image a cat or a dog? But whereas like what we're doing with semantic segmentation is we're trying to determine like which pixels corresponds to a cat or which pixels correspond to a dog exactly in the image. So it makes sense that we kind of want our output to have the same resolution as our input. So that's why we have to like upsample like after we downsample like at the beginning. So yeah, I think I see some activity in the chat. I'm not sure if those are like actually questions or let's see. How would the code look different for the Inception or UNet model? Actually, like, I mean, you can like, I think for a UNet model, you can definitely still use like either PyTorch or Keras API to implement, but as for Inception, it will be Yeah, but you can still like combine these in parallel. So it's definitely like a little bit more involved than just like the CNNs that we implement as an example, but it's definitely still doable with like the right combination of like or the right APIs. So you don't have to implement everything from scratch. Yeah,
Would you
go
just
ahead.
have to like, for instance, if you're using one of the libraries, either PyTorch or TensorFlow and Keras, would you just have to specify that you're using like a model where it would be running in parallel, I guess? Because it's not like
That's a good
linear,
question.
or I don't want to use the word linear, but it's not like following each step, at once. It's running several models and then doing them in parallel and then combining.
Yeah, I think I see what you mean. So I guess there's like, especially with Keras, like there's not an easy way to do it, but actually like haven't had the chance to look at the code for these models.
Yeah.
So I'm not sure how they implement them exactly. But I'm assuming there
So-
has to be a way to
So
be a way to
in-
combine.
Right. I think in PyTorch it'll be pretty simple to implement, because you see, we define the forward prop function ourselves, right? So we define each of these pieces, we define our x, pass it through each of the pieces, and combine them at the end. So in PyTorch at least it seems possible, and I'm not sure exactly how it's defined in TensorFlow though.
Yeah, I mean, at least in TensorFlow,
Yeah,
I think there you can kind of define if you want your layers to be sequential or parallel. So I'm not too sure about how to work with that because I've not really looked into it too much, but there might be a way to, like, if you want to like parallelize certain layers, you might be able to declare like, oh, I want the next few layers to be parallel, and then add those layers to like that parallel layers object, I guess. But yeah, I think that's just a thought I had. But yeah, keep going.
Yeah.
Got it. Sounds good. Thank you.
Okay, cool. All right, so next we're going to be covering one by one convolution. So I'm going to pass the time to Adithya.
Alrighty. See this up. All right, fantastic. Okay, so before we begin, I think because at least for this example for one by one convolutions, we're going to be talking a little bit more about input volumes rather than just input 2D inputs. So because I think that we need to make a distinction between these two keywords, which are kernels and filters. There is a aura of ambiguity that surrounds these two words in the CNN community. When we talk about like kernels and filters, they're often used interchangeably, and that has like led to confusion in the past. So in order to avoid that right now, as we move forward, I think it's a good idea to kind of like define concretely what kernels and what filters are and how they're different. So yeah, sorry. We can think of filters, like as we discussed in the previous workshop, as volumes of weights. And the reason why these filters are volumes is because oftentimes you receive an input volume, and in order to convolve over that input volume to extract features, we need to use a filter that has the same depth as the input volume. So let's say you receive, like from your initial layer, you receive an image of like spatial dimensions 500 by 500, and you receive, and the input volume of that input, the depth of that input volume is like, let's say 3, which corresponds to the 3 RGB channels, red, green, blue, that we use in everyday pictures. In that certain sense, your filters you use will have smaller spatial dimensions. You can kind of focus on the different features in that image, but they would have to have that same amount of depth, which in this case is going to be 3, so that you can convolve over that input volume, which also has a depth of 3. So yeah, so you can think of filters as volumes of weights, and you can think of kernels as slices of that volume. So you would often talk about kernels in a 2D sense, just to say it like the least. So when you define a kernel, you might say like, oh, this kernel is a 5x5 kernel or a 3x3 kernel. But when we're talking about filters, especially in the sense of these sort of input volumes you receive when you deal with number one, pictures that have color, like the RGB channels, as well as like you might have like input volumes from one convolutional layer with like 256, a depth of 256 for all those different filters you use. So yeah, just a real quick like clarification as we move forward. Think of filters as volumes of weights, and think of kernels as slices of those volumes. So if you have a filter of like, let's say 5x5 by 256, you have that 256 as the depth of the filter, but the kernel is going to be that 5x5 spatial dimension. So yeah, we're going to just keep going with that as our sort of definition of kernels and filters. So let's move on to the actual topic here, which is one-by-one convolutions. The issue with having large kernels like this, and especially with having this immense depth to our input volumes at different points in our convolution in our convolutional network, is that you end up in a situation where you need to train a whole bunch of weights. And that involves a much larger training time, a lot more calculation is required at that point in time. So let's take, for example, you get an input volume of, let's say, 500 by 500 by 256. So your depth of your input volume is huge. It's 256. Your filters, let's say you take a kernel size for your filter of 5x5, and your filter depth needs to match the depth of your input volume. So that means you have filters which are essentially 5x5 with a depth of 256. And let's say you want to focus on 256 distinct features. You would have to have 256 of these filters. So that means you're going to be having 5x5 by 256, which is the volume of one single filter, multiplied by 256 for those 256 different filters. So if you think about it, that's a lot of weights, 5x5 by 256 by 256, really big. That's going to be a lot of computation, a lot of training time, which is an issue. We don't want to take forever to train our models. And we don't want them to be too computationally intensive. So yeah, it's a lot. And how do we deal with that? Well, we have this concept of one-by-one convolutions. Essentially what one-by-one convolutions are is that they're essentially filters with a kernel size of just 1x1 and a depth that is often 1x1. And the reason why these help, and we'll get an example right now, is that they compress the depth of the image of the input volume. They compress it so much that you still maintain the information that picture holds, that your input volume holds, but you have to deal with a lot fewer weights, like a lot fewer. And we'll get into an example right now. So as we said in the previous example, if you had if you received an input volume of, let's say, 500 by 500 by 256, so your 256 is your depth, and you apply a kernel size of 5x5, and since you need to maintain that depth as the same depth as your input volume, you need to use a filter that is 5x5 by 256. And you want to use 256 of those filters. So again, the same calculation we got, 5 into 5 is 256. lots of filters in the millions. Now let's use one-by-one convolutions. That's going to essentially, we're going to basically be introducing with these one-by-one convolutions a sort of intermediary layer or step that's going to like help us reduce the dimensions of our input volume. And the way this works is pretty interesting. I think I explained this kernel. We can explain one more time. Yeah, for sure. So yes, yeah. So this is why it's like it becomes important to make that distinction between kernels and filters, because once you begin talking about these input volumes, that's when like things get a little bit more complicated. So yeah, think of a filter as a volume of weights. And so like, as I said, for example, oftentimes you would have a filter which needs to match the depth of your input volume. So let's say your input volume is 500 by 500 by 256. That means your input volume has spatial dimensions of 500 by 500, and it has a depth of 256. Because of that, you would require a filter, and the key word here is filter. You would need a filter that has lower spatial dimensions. So instead of 500 by 500, you might take maybe like 30 by 30. So your spatial dimension is being reduced. And the reason why you're doing that is so that you can focus on specific features in this input volume. But your depth needs to match the depth of your input volume, which was 256. So that means your filter is, as we said before, which is a volume of weights, is going to have dimensions 30 by 30, which are the spatial dimensions we chose, into 256, which is that depth. So when we talk about filters, we want to talk about volumes of weights. Yeah, so it depends on what the depth of your input volume is, whether you're coming from the input layer, which usually, so your images have an input depth of 3, or at different points in the CNN, which might have much larger depths. So the deal with filters is you always talk about filters in the context of volumes. So you have spatial dimensions and the depth. You can think of kernels as slices of those volumes. So when we talk about kernels, there's no real concept of a depth to a kernel. A kernel is just a two-dimensional matrix of weights, which is essentially just a slice of your input, of your filter, essentially. So your filter has depth, and each of the slices of your filter are different kernels of that filter. I hope that made it clear, because it's a little hard to get your head wrapped around, and it takes some time to like absorb this information and move forward. But yeah, just think of filters as, okay, perfect. Yeah, filters are just volumes of weights, and kernels are essentially just slices of those volumes, which make them two-dimensional essentially. So yeah. Okay, cool. So we talked about all these weights that you would need to train if you did not apply one-by-one convolutions to get dimension reduction. So let's use one-by-one convolutions and start applying dimension reduction. So again, let us imagine we are receiving an input volume of, let's say, 500 by 500 into 256. So your depth is 256 for your input volume. Now let's use a one-by-one convolution. So that one-by-one convolution tells us immediately that our kernel size needs to be 1 by 1. So we have a 1 by 1 kernel size. And again, because the depth of our input volume is 256, our filters need to match that particular depth. So our filters will have dimensions 1 by 1 into 256, right? And oftentimes when you use 1 by 1 convolutions, the main goal is to compress the image, to compress the depth of the image. So that's what we do. We might take like 64 filters, for example, and that's going to compress the output, the depth of our output volume essentially. Also keep in mind that 1x1 kernels don't really interfere with the spatial dimensions of our input volume. So we talked about our input volume, in this case, having spatial dimensions of 500 by 500. That spatial dimensions are going to be preserved with 1x1 kernels, because if you think about it, if you just have a 1x1 like just a singular weight, essentially a 1x1 kernel convolving over an image, you're literally just taking that single weight or that single value of that 1x1 kernel, and you're just like kind of multiplying it with every single value in that input volume. So the 1x1 kernels don't mess with the spatial dimensions you receive. And that's kind of what we want. We want to maintain the spatial dimensions. Our goal here is to compress the depth of the image. So cool. So we have an input volume of depth 256. This leads us to have filters which are 1x1 by 256 to match that depth, and we only use 64 filters. Great. What does this give us? Well, we're now, because of that, we are maintaining our spatial dimensions, but now we've compressed our output volume from this intermediary layer to 64 instead of 256, which is already a huge leap in kind of compressing the data our input volume holds. And after that, that's when we can go back to applying our 5x5 kernel. So now in the next portion, we receive an input volume that is, let's say, like 5,000 by 5,000 to maintain that spatial dimensions. But now our depth is shorter. It's 64 instead of 256. So now if you think about it, in our next layer, our kernels, let's say they're 5x5, but now our kernel, our filter depth needs to be 64 because the input volume we're receiving is about 64. And that actually leads to a huge reduction in the number of weights that you see. So to talk about numbers specifically, in the first example, without using dimension reduction, the number of weights you're seeing is going to be essentially going to be equal to 5x5 into 256 into 256, which gives us about 1.6 million weights. But after we apply dimension reduction using 1x1 convolutions, we get 425,000 weights. And the reason for that is so if you look at the first sort of layer here, where we deal with these 1x1 kernels, we have 1x1 by 256 filters, and we have 64 of them. So essentially, our first calculation here is 1x1 into 256 into 64. That layer has those many number of weights to train. In the next portion, since our output volume has a depth of 64, these filters will have dimensions 5x5 into 64, and you have 256 of those filters. And adding those two values up, the number of weights to train in the 1x1 convolution layer and in this normal sort of 5x5 kernel layer, adding those together up gives you this value of about 426,000 weights, which is a huge reduction in the number of weights that we have to train. So yeah, it is a little bit convoluted. It's hard to kind of wrap your head around what's going on, because you think about like these sort of volumes and how these filters kind of convolve over those volumes and all that sort of stuff. But if there are any questions right now, this would be a good time to bring it up. So yeah, are there any questions?
Real quick, what's a voxel again? On the slide.
Okay, yeah. So so a voxel, I believe. Yeah, so a voxel is essentially just, it's essentially what you call a 1x1 convolution. A voxel is just like a filter with a kernel size of 1x1, but that has some amount of depth to it. So yeah.
Can I jump in real quick?
Mm-hmm.
Yeah, so essentially a voxel. Okay, so when you have like some matrix, right? One of those points in that matrix is a voxel. So you have like some x coordinates, some y coordinates, some z coordinates. Just one of those little pixels in your matrix. So that's a
Mm-hmm.
kind of a generalization of a pixel, if you think about it.
Okay. Yeah. So yeah, you can think of it as just like one value in our input volume, because our input volume is already this sort of like 3D volume of like values. You can think of a voxel as just one value in that sort of volume of values. So yeah.
Got it. That makes sense.
All right. There are no more questions. I'm gonna go here. It's a bit of a challenge, I would say. But definitely try giving it your best shot. I'm gonna like launch this poll. Let's see. Yeah. So yeah, so the poll is live. Take your time. I'll give you guys like maybe 2.5 minutes or so based on how people do this. How many people complete, and yeah, just take your time, read the question carefully, and go for it. Feel free to use calculators and stuff if you guys want to, but yeah, feel free. All right, we'll give it about 30 more seconds. All righty, we can end the poll off there. And let's share those results. So yes, definitely a challenge question for sure. And the answer is B. And we'll go over this calculation actually real quick, so that everyone can understand how it works. But yeah, so let's look at the question. We have spatial dimension. So we receive an input volume first off, with spatial dimensions of 1,000 by 1,000, and depth of 512. All right. So we want to reduce its dimensions. So we use 32 filters, each with the kernel size of 1 by 1. So that's our first clue. Our kernel size is 1 by 1. That's like our first clue. So if that's our kernel size, we need to calculate what the depth of our filter is, because we know the spatial dimensions of our filter now. It's just 1 by 1. What is the depth of our filter? Well, it's going to be the depth of the input volume that we received. And the input volume we received had a depth of 512. It's mentioned in the question right here. Great. So we know our filter. Our filter dimensions are 1 by 1 by essentially 512. Oh, this is embarrassing. I made a boo-boo in the question. Yeah, this is embarrassing. This 256 is meant to be 512. So this poll is null and void. I made this at like 1 a.m. yesterday, well, 1 a.m. my time at least. So I was a little bit wonky, but speaking to continue, but yeah, just to go over this calculation, since you have kernels of 1 by 1 and your depth needs to be the same as your input volume depth, which is 512, and so now we know the dimensions of our filter, which is 1 by 1 by 512, and we have 32 of those filters. So we know like our first piece of our calculation, the first piece of our puzzle, we have weights. The number of weights are going to be 1 by 1 into 512 into 32, which should have been D, but 256. My bad. But yeah, so that should have almost like given you a clue about like how to progress. And after that, we take a look at our next layer. And the next layer, it says we have 5 by 5 kernels and 256 of them. What this tells us is the spatial dimensions of the filter in our next layer is 5 by 5. And since we need to, again, match the depth of our input volume, the input volume from the previous layer had a depth of 32 because that's the number of filters we use. We use 32 filters. So that means our filter dimensions are 5 by 5 by 32, and we're using 256 of those filters. So we like multiply that value again by 256. And that's what we see here, 5 by 5 by 32 into 256, which, since I did a boo-boo here, this is probably going to be a bigger value. So my bad with that, but I hope you guys kind of like understand where this is coming from and why we do this sort of thing using 1 by 1 convolutions to reduce the dimensions. Because if you take a look again at how we, the number of weights that we had to use in our, without using dimension reduction, that's about 1.6 million. And now we're reducing it to about 420,000. So it's a big reduction in computation time and training time, and it makes a life a bit simpler. So yeah, sorry about this. I don't know why that happened, but hopefully it won't happen in the future. But yeah, I hope you guys understand how dimension reduction with 1 by 1 convolutions work. All right, let's just quickly get into classification, detection, and segmentation. It shouldn't be too hard, not too crazy as 1 by 1 convolutions. So yeah, this like gives you a really good understanding of what classification, detection, and segmentation are. Classification, you are just labeling an image. You're saying like this image is either this or this, dog or not dog, cat or not cat, blah blah blah. So yeah, that is classification. We have detection, which begins to implement these sort of like local detections, I guess, of the image, where you can kind of identify different aspects of the image as being in a certain class. In this case, we're looking at this dog in this image, and we can identify that this what this thing is in the picture is a dog. We can classify it as a dog, and we can apply a sort of bounding box to that. And segmentation takes it a step further. Now we're labeling pixels. And when we label pixels, so when we're labeling pixels, we can immediately say like I know that this pixel is from a dog and this pixel is not from a dog. And you can really kind of like figure out what each pixel in an image really is a part of, if it's a part of a particular class or if it's not. So yeah, fairly straightforward, I would say. Are there any questions about this? All righty, let's move on. Let's go a little bit quicker. So yeah, segmentation broken down into a few more classes. We have regular semantic segmentation and instinct segmentation. Tells you pretty simply, pictures tell you what they mean. Regular semantic allows this sort of segmentation of the image into these different classes, but you can't really tell if these classes are different or not. So the only thing that happens is you can tell if a pixel is a puffin or not a puffin. But with instant segmentation, you take that a step further and you realize that, oh, this puffin is a puffin, but this other pixel is also a puffin, but it's not from the same puffin that I saw earlier. So it's a different puffin, and you can do that with different number of puffins. So yeah, that's just instant segmentation. You can locally identify and distinguish between different instances of the same class. And these tasks are well suited to be performed by the UNet CNN architecture that Jenson talked about earlier. Yeah, one other thing that we've been talking a lot about pooling and using filters and this one-by-one convolution and how that really helps us reduce the dimensions of our input volumes and makes things simpler for us. But we as humans, we want to see things in the way we see it. We don't want to see an image of like really low spatial dimensions of like 50 by 50, but a depth of like 512. Like we don't really know what that is. We want to see images in the way we see them, and that's where this concept of upscaling comes in. We want to scale our image. We want to scale our input volume up so that it matches the initial sort of input volume we receive, which is usually these really large spatial dimensions for these high resolution images, but with a depth of like 3 for like RGB channels. So this concept of upscaling kind of it applies in the sort of like the increasing section of that UNet architecture we saw earlier, where we're kind of like taking like these input volumes, which are very thick, has a lot of depth, but not too much spatial dimension, and kind of like upscaling that to match images that we see on a daily basis. And this is known as transpose convolution or deconvolution because it's often the inverse of convolution, like like convolution and filtering and all that sort of stuff. So yeah, just like quickly tell you guys like how this, so like, yeah, so if you see the bottom of this U here, we have these sort of like chunky 28 by 28 spatial dimensions, but like really thick in terms of depth. And transverse convolution applies when we're kind of like going up this U to eventually get these sort of like output images which are closer in dimensions to our input image. And that's where transverse convolution comes in. We're going to see how this works in a second. So yeah, this is a very simple example of how transverse convolutions work. Again, this is just like a 2D image output, a 2D image and a singular kernel. So it's a very basic example, but the way it works is let's take a look at the top left corner of our input. We have our kernel, which is 2, 5, 6, and -2. We do a sort of element-wise multiplication with that kernel. So that means the kernel remains the same because our value is just 1. And we kind of stick it in this 3 by 3 grid in the top left corner to like reflect that it's representing this sort of 1 from our input, which is also in the top left corner. Yeah, the input is actually a feature map. Yes, it's a feature map because remember, we are kind of upscaling. So it's so yeah, at that point, we're only dealing with feature maps. Yeah, and then you kind of do the same thing with all of the different input values we have. So we have that 2, which is in the top right corner. So you kind of multiply 2 with every single kernel value, and you stick it in the top upper right corner of this 3x3 grid. And you do the same with the 3 and the 4. You're doing this element-wise multiplication, and you're sticking your result in that same corner of the 3x3 grid as you got from the input. And yeah, and so you get these like 4 sort of intermediary 3x3 grids, and like just assume that the blank squares are just zeros. Next thing you do is just add each position in the 3x3 grid with corresponding values. You keep adding them up, and you get your final result, which is essentially just a scaled up version of the input, but it's also sort of highlighting the feature that this kernel is representing, whatever feature that kernel represents. So yeah, this final result is, and it encodes information about both the input you receive, which is 1, 2, 3, 4, as well as the kernel. And as you can see, the final result has dimensions that are greater than the input. And that's the whole point of transpose convolutions. So yeah, it's not too much. Don't like fret too much if you like don't really understand it. It's just something that you should know, that there is also a process of upscaling when we're doing CNNs, because we've only been talking about downscaling. But yeah, there is also this idea of upscaling images so that they're viewable by us, so that we can like identify these sort of like segments that we talked about earlier with the puffins and stuff. So yeah, are there any questions about this? Alrighty, cool. Well, in that case, I believe that's it from me. Yep, I'll hand over to Sudhanshu.
Okay. Can everyone see my screen? Yes. Okay.
Yeah.
Cool. So now we're going to talk about another type of architecture called residual neural networks, or ResNet's for short. And this is actually a very, very cool architecture. And it's pretty much in the real world. Whenever you're training a very deep neural network, you're going to want to use ideas from this architecture. And so let's start with some motivation, right? Suppose we have this neural network right here, perfectly good neural network. And we decide, you know what, I have a lot of time in life, I have a lot of compute power, I have a lot of money, I have funding, I'm going to add like 100 more layers to this neural network. And we think, yeah, you know what, more layers, more accuracy, right? So we do that. And what happens? We see that the deeper network doesn't necessarily achieve the better performance. So in theory, it doesn't make really any sense, right? Like we've been taught, oh, more weights, more parameters, better accuracy, better learning, whatever. Deeper is better. But that's not really the case. And the reason is what we call the degradation problem, or the vanishing gradient problem. So this is an image right here from the paper that came up with this, the paper that came up with ResNet's, where they show that actually a 56-layer neural network had a higher had a higher error than a 20-layer neural network. So even though you added those extra 36 layers, you actually ended up doing much worse. And the reason we do that, the reason that happens rather, is because of the vanishing gradient problem. So you see this is like a little visualization, the gradient starts vanishing. So what really is the vanishing gradient problem? Now, if we go back a sec, we have this neural network right here, right? And it could be like 150 layers deep easily. Now, what we're doing during backpropagation is taking that one gradient value, taking it back to each and every layer. So we're taking it all the way back across all 150 layers. Now, what is the gradient really? The gradient is how much each layer contributes to the overall cost. If you have 150 layers, each layer is going to contribute very little to the overall cost. So the gradient becomes very, very small and ends up vanishing. Now, why is that an issue? Well, the gradient is the only thing that allows us to update our network. If the gradient is 0, we don't update our network. So if we don't update our network, well, we're not doing anything. We're not training, we're just sitting around waiting for the program to end. So vanishing gradients is a very big problem. And ResNets are an attempt to kind of fix this. So the intuitive way to understand it is that information ends up getting lost the deeper you go. So what are ResNets? So now ResNets work by these blocks, which we call residual blocks. So suppose, let's consider for a second just this inner image. We have our good old-fashioned neural network. We have an input X multiplied by some weights, activate ReLU, multiply by some weights, activate by ReLU, so on and so forth. Seems all well and good. But suppose this little section was layer 100 in our neural network. So way back in the previous 99 layers, we've done a lot of really good stuff. We've detected some edges, some corners, detected an eyeball, we've classified dogs, all that other good stuff. And we're like, okay, let's add a couple more layers, try and really detect that edge really carefully. Now, the issue is, right, so our X over here is actually pretty good. It's pretty good result already. And now it goes to this weight layer over here. But suppose we had this vanishing gradient problem. Our weights haven't been updating in this layer. And basically, all the values in this layer are pretty much 0. So this weight matrix has very, very, very small values. So this nice X that we just got from here gets multiplied with this weight matrix and ends up becoming so close to 0. So all that work just kind of goes to waste because of this one bad layer. So then we pass it through another weight matrix, and guess what? It gets even worse because we're multiplying by another smaller number. So we start off with a pretty good X. We go through these layers and we end up with a pretty terrible and pretty small value. So residual networks try and overcome this. So let's try and do some thinking. We have an X value with some pretty large values in this matrix. We have an output with some pretty small values in this matrix. I want to make this output larger. What should I do? Well, kind of a stupid answer almost is, let's just add this big value to the small value, give it a boost. And you'll be like, okay, hold up. You can't just add the input to the output. It doesn't make any sense, right? And frankly, yeah, that's how it seems intuitively. But let's try and think a little bit about why this would actually work. So what we're doing is we're taking X, multiplying by W, we get some layer value, some layer output value. Sorry, one second. Oops, okay. Sorry, so we have some X, we pass it through some weights, we get some layer output. We multiply by some more weights, we get some other output. And what we do, we simply add X to that output. And this serves as the input to our ReLU or tanh or sigmoid. So what's really happening here? Suppose these weights become very, very small. This W becomes small, this L1 becomes small. What happens? This term tends to 0. So this map ends up becoming just the identity map, because X, the input, goes all the way through the identity and produces the output. So in the case that our layer, the weights were really, really bad with just zeros everywhere, we haven't really done anything. We haven't really messed up our network because, hey, who doesn't love the identity map, right? X goes to X, we're fine. So in the best case, suppose our weights actually work, we got some really cool features, we detected an extra corner, that's fantastic as well. We add that extra information in, everyone's happy. But the important thing to note is that it can't get any worse. So these layers won't be able to mess up your entire training in the last 99 layers. So if the weights go to 0, the layer just this entire block becomes the identity map. Okay, that was a lot. So does anyone have any questions at this point? Does this sort of make sense? I'll go over a summary of this in the next slide. Okay, I think we're good. Yeah, okay, awesome. So so basically, in theory, right, this network should perform at least as well as a shallow network. Why is that? Because in the best case, we have an extra layer, and in the worst case, we haven't done anything. So, so the real issue that we were facing before is that all the work we were doing gets kind of destroyed. So the advantage of this is that in the worst case, the network decides, I don't really need those extra layers. I'm just going to take all these weights to 0 and say, you know what, I'm done. I'm going to go home for the day. And that's kind of where the ResNet makes a big difference. So if you have like 100-layer neural network and you're passing all these values through, and the neural network decides, okay, listen, I'm done learning. I only needed 50 of those layers, right? Why are you giving me another 50 layers? It's just going to say, okay, I'm going to have an identity map at that point. And that's how this helps. Okay. Are there any other questions? Did that help any at all? Zero. So we have a question. Is this related to zeroing the gradient? Not really.
I don't know what zeroing the gradient exactly is, but I was reading up on some article, and it mentioned this, and so I was kind of curious if this was the same vanishing gradient issue or like if they were somewhat related.
Okay. I think okay. So I think zeroing the gradient, when you say that, that's kind of something we do, right? As programmers, we say, I don't want to update these layers. I'm going to zero out the gradient for those layers. This is a different thing. Vanishing gradient is a problem that we're trying to solve. So I'm guessing that zeroing gradient, I'm not sure with exact term, but that's something we do as a conscious choice, right? But vanishing gradient is a problem that we're trying to fix here. So yeah, I'm pretty sure they're different.
Got it. Sounds good.
Mm-hmm. Any other questions? Feel free to ask any question. This is a pretty important concept in deep learning, and it's one of the biggest advancements in training of CNNs since God knows what. Yeah. Okay, I think we're good. So yes, the main application is to train these very deep neural networks. But actually, a very interesting application of ResNets, something that came up in the last couple of years, is actually solving differential equations. And this seems completely non-intuitive, but trust me, the reason is actually very, very cool. So a couple of years, actually 3 years ago, these guys came up with an architecture called neural ordinary differential equations. And so this architecture uses ResNets to solve differential equations. And it was such a great idea. It won the best paper at the NeurIPS conference in 2018, which is kind of the most prestigious conference in all of machine learning. So it's a really, really cool idea. And what they basically observed is the following, at a high level, of course, is that we have this x, which passes through some function. So we have some f of x at the end of it. When we pass in our residual connection, we pass in this x, we get f of x plus x. Now, if anyone's taken a course in differential equations before, you might have come across something called Euler's method of solving differential equations. It essentially says, take some x as a starting point, take some function of x, technically the gradient, and add that to X. And that way you can kind of move along a curve. So what these guys observed is, hey, the ResNet looks a lot like Euler's method, like, big brain time. So they kind of use this in a more complicated way, of course, to solve differential equations. And this became a really, really popular idea. In fact, as an aside, my research stuff is kind of involved in this area, so that's why I know a little bit about it. But this is just an aside. ResNets are a really, really cool architecture, and it's a pretty important concept. Awesome. So, we have a question here. Is this how Wolfram Alpha solves ODEs? No. So this is, I'm pretty sure Wolfram Alpha, I don't know exactly, but I'm pretty sure Wolfram Alpha uses the traditional methods like Euler's method, like RK4, to solve the differential equations. Okay, any other questions? Yeah, this is just an aside. No one would expect you to think about this. So it's just an aside. Okay, so let's do one more concept, which is called transfer learning. Now, this is also actually very important in the real world. And I'm going to try and kind of paint a picture of when we'd use this. So suppose tomorrow, I decide I want to make a new app. I want to take a picture of a dog, and the app will tell me which breed the dog is. It's a fair enough application. And then I do some thinking. You're like, okay, wait. 5 slides ago, Adithya just told me that I'm going to need 1.6 million parameters to train this model. And I'm sitting here on my tiny little laptop with Intel integrated graphics. I can't really train that. So what I decide is, hey, someone somewhere has probably trained a pretty big neural network using images of dogs. Maybe they've tried to classify dogs and cats. Maybe they've done something else, filters. I don't know. But somewhere has created a neural network which has been trained on an image, on a data set of dogs. I want to take those weights, those trained weights in the neural network, and use it for my own project. And that's what transfer learning helps us do. So if I wanted to just create a brand new neural network with 150 layers, initialize it randomly and train it from scratch, I don't have that kind of time. And we need a lot of data, at least a few million images, which aren't that easy to get. So the solution is to use a model that was pre-trained on some images. And we use that model as a starting point and build our project from that point on. So we're essentially transferring the knowledge from one network to another. Now, at a very high level, we have a couple of different ways in which we can do transfer learning. So one method is to just say, okay, someone somewhere has created a neural network with 10 different layers, trained it, uploaded the weights. So what I'm going to do, I'm going to create that same exact neural network, download all the weights, and use that as my starting point. So in the beginning, instead of saying, initialize weights random, I say initialize weights to that saved file. Simple as that. And I go forward and train my neural network from that point on. So that's just pre-training, and then you just push it. You just train it to that last final stage for your application. Another method of transfer learning is by freezing layers. So again, you download your neural network, your pre-trained neural network, and you freeze a certain section of that neural network. So I freeze some portion of it, and then I just train the final few layers for my application. So that's another way to perform transfer learning. Okay, any questions about transfer learning? Okay, I think we're good. Okay, so let's try and open it up some discussion, right? So the first question we have is, what problem do residual blocks address? So we covered this 10 minutes ago, but what kind of problem do they address at a high level? Type it out in the chat or unmute. And like I said, ResNets are important. You might, who knows, you might, get the best paper at NeurIPS next year. Okay, getting some answers. Okay. Yeah, so we have the answer in the chat, and they solve the vanishing gradient problem. And that's absolutely right. So they essentially short circuit some connections to ensure that the layers affected by the vanishing gradient problem don't mess up the network. So that's absolutely right. So the second question, yeah, so actually wait, first before that, does anyone have any questions about why that's true? Why do the residual networks solve the vanishing gradient problem? Okay. I think we're good. So the second question, how do transposed convolutions help? So this is that deconvolution that we discussed just before. And what do they do essentially? Okay, that's a good intuition. Do you remember the technical term for what you just said? Yep. That's exactly right. So it's so transpose convolutions essentially help us upsample. So we essentially had this downsampling. That's the entire purpose of convolutional networks, to keep downsampling. But what transpose convolutions do is upsample. So they go from small to big. And that's helpful because we often, we get so lost in that gigantic process and we have this tiny little activation at the end. We want to finally upsample that to produce an actual visual image. Okay. I think that's it. Are there any other questions? Okay. Awesome. So we have the answers to all these discussion questions along with a few other questions in this worksheet. Feel free to check that out. But that's it. So by the way, we're having a social this Saturday night. So it's open for any UCLA students. Feel free to come out and hang out. We can play some games. I think Among Us, Jeopardy, something like that. So it's gonna be a lot of fun. This is the Facebook event. And thank you all so much for coming. Feel free to stick around if you have other questions. Please fill out our feedback form. And yeah, also we have office hours after this in the ACM AI Discord channel. So feel free to stop by if you have any questions about AI or anything else.
Thank you, guys. Good stuff.
Yeah, thank you guys for coming. Have a good rest of the week.
Midterms, bro, midterms.
Okay.
Oh, wow, that was quick.
Alrighty. Yeah, everyone dipped. Oh my God, I did the biggest.
You want to stop the recording, Jenson?
Oh, yeah.